Alright, so in this video, we're going to focus on electrons, and specifically we're going to look at wave-particle duality of electrons and electron configurations. So electrons are important to study because they tell us many things. For instance, they tell us or help explain periodic trends, reactivity, and they also help us understand electromagnetic radiation such as light. So this idea of wave-particle duality says that particles can act like waves and waves can act like particles. So since we're going to begin talking about waves, we're going to first define some characteristics of waves. The first characteristic we're going to look at is wavelength, which is represented by this lambda. It's kind of like an upside down Y. So the wavelength is going to be the distance between corresponding points on adjacent waves. So here, the wavelength is drawn from the top of the wave to the top of the next wave. So we call those tops crests, and then the bottoms are called troughs. So for a wavelength, you can measure crest to crest or trough to trough. Now, the wavelength values you could be given could be in nanometers or meters or any kind of prefix of meters, but for our calculations we need this to be in meters. Okay, so a lot of times the waves we'll look at have really small wavelengths and they'll be in nanometers, but to go from nanometers to meters you can use this conversion factor. 1 nanometer is 10 to the negative 9 meters. So if you have nanometers, multiply it by 10 to the negative 9 to get that in meters. All right, the next characteristic of waves we're going to look at is frequency. So frequency is the number of waves that's going to pass some given point per second or per unit of time. But our frequency we're going to measure in units of hertz, which is going to be represented with an Hz, or that's also equal to 1/second, like inverse seconds. Okay, so wavelength is the kind of like a length of a wave, so crest to crest or trough to trough. Frequency is how many waves can pass through some point per unit of time. So if we marked like some point here, say this X spot, we're going to count how many cycles, how many of these waves can pass through this point each second, and that would give us the frequency. So as you could hopefully predict here, so we have two different waves. Let's call this top one A and call this bottom one B. A is of course going to have a much shorter wavelength, as we can see in this picture here, whereas B would have a longer wavelength. However, if we were to look at the frequency of both, hopefully you could visualize that more waves of A can pass through this point each second than B. What that tells us is that frequency and wavelength are inversely related. Okay, so the larger the frequency, the smaller the wavelength, and vice versa. Now, this letter that we use, our variable we use to represent frequency, it looks like a V, but it's actually a lowercase nu. All right, so all of our electromagnetic radiation, we're going to say is going to travel at the same velocity, and that's this constant that's often represented with AC, and it stands or represents the speed of light. Now, here I have it listed as 3.00 times 10 to the 8th, but on your reference sheet it actually listed as 2.998, I believe, times 10 to the 8th. So what you'd want to do if you're making a calculation is actually use that reference sheet value you have there. And this equation here that relates the speed of light to wavelength and frequency is also on your reference sheet. But C is going to be in meters per second, and that's a constant. Wavelength is going to be in meters, or it needs to be in meters, and frequency is going to be in hertz, or like I said, inverse seconds. Okay. So what this equation allows you to do is, if you're given the wavelength, you can find the frequency using this relationship here. All right. Now, wave model of light is awesome, but it does have some flaws, and it doesn't explain several concepts such as black body radiation, photoelectric effect, and emission spectra. All right, so instead we're going to use another relationship, which is going to relate the energy of a photon, to the frequency of that photon. All right, and each of these photons, again, is going to have an energy equal to, it's related to the frequency, but more specifically, it's going to be equal to h, which is going to stand for Planck's constant, times that nu, which again, here in this case, is still frequency. So you could use this equation, which is also on your reference sheet, and Planck's constant is on your reference sheet as well, to make calculations for the energy of a photon or energy of a wave or frequency. And in some cases, you might have to use both this equation and this one. Because say, for instance, you're given the energy and it's asking for the wavelength. Well, you don't have one equation here that has both of those variables in it. So what you would need to do first is start with your given, which is energy, calculate the frequency, and once you have frequency, you would substitute that in for the frequency in this second equation here, the C equals lambda nu, and then calculate your wavelength. All right, so some take-home messages from these things is that radiant energy is going to be quantized, so as in we can assign numbers to these things. Light can act like both a wave and a particle, and energy of light is related to its frequency. All right, so let me jump ahead here to, so again, these energies are related to frequencies, and what the Bohr model did is it quantized the atom. So what it said is these electrons travel in these paths around these nucleus, around the nucleus, and those paths have specific energy values associated with them. So electrons are arranged in these paths based on energy values. And all of those energy values are going to have specific frequencies associated with them. And this also helps explain stuff like the flame test. So when we heated up different metal solutions or metal salt solutions, the flame would change colors. And the reason that it changed colors is each of those elements are going to have their own unique electron configuration. So when we excite them, they'll jump to different energy levels. And as we just saw, energy is equal to h nu, so energy is related to frequency. So different energies are going to give us different frequencies, which give us different wavelengths, which means we have different colors. All right, now before we get into electron configurations, one thing I do want to mention, and I'll talk about this too in later videos, or specifically the video on intermolecular forces and Coulomb's law. But this Coulomb's law, it explains the attractive or repelling force between two charged particles, which we'll label as Q1 and Q2. And what it says is that force is directly proportional to the size of those charges and inversely proportional to the square of the distances between them. If Q1 and Q2 have the same sign, then that force is going to be repulsive, right? Because like charges repel. Or if Q1 and Q2 are opposite signs, so like Q1 is a positive charge, Q2 is a negative, then that force is going to be attractive. But what this says is if you have two charged particles the closer they are, so as we decrease this R value, this whole fraction is going to increase. So the closer those two charged particles are, the greater that force is between them. And this numerator tells us the greater the size of the charge, the greater that force. So for instance, if we're looking at Na plus, here, let me write this out. If we are looking at Na plus, and we have over here chlorine minus versus an Mg2 plus, and still that chlorine minus, the magnesium ion would have a greater attraction to that chloride ion because there's a greater charge. So if magnesium, or if these cations were the Q1, magnesium would be a +2, and then the Q2 would be a -1, whereas with sodium chloride, it would be a +1 and a -1. So magnesium chloride, or magnesium, we would expect to have a greater attraction to chloride compared to sodium. And we can also use this R squared term too. As you'll see in the next video, the atomic and ionic radius is going to generally decrease as we move from left to right. So magnesium is going to be a smaller, or the magnesium ion is going to be smaller than the sodium ion. So what that means is there's less distance between the magnesium and the chlorine, which means this attractive force between those ions is going to be bigger. All right, so again, Bohr quantized the atom, and he said that the electrons are arranged in these fixed paths around the nucleus, although now we know that that's not completely true. Instead, these electrons are in these probability orbits, as described by the electron cloud model. So what Bohr's model allows us to do, though, instead is, again, we have these electrons in these paths. If we excite them, so like give them energy, they can jump up to a higher energy level. Once they're in this higher energy level, we say that's the excited state, because it's in an energy level other than what it typically is found in. So it's a higher energy level. But eventually, it's going to relax and return back to the ground state, the state it was originally in. But when it relaxes and returns back to that ground state, all of that built up energy is going to be released. And it could be released, or often is released, as a photon, and it could be in the form of light. So again, that helps explain the flame tests. All right, let's jump then to electron configurations. So again, Bohr said that the electrons were in these fixed paths, but the electron cloud model says they're in these probability orbits. All right, sorry, I'm jumping ahead a bunch here. All right, so these electron configurations are tied to these sublevels. So it's tied to a principal energy level, and then it's also tied to these sublevels. The number of sublevels that fits in a principal energy level is related to the value of the principal energy level itself. What I mean by that is the first principal energy level, which corresponds to period 1, is going to have one sublevel in it only. So principal energy level 1 has one sublevel, and that's just an S. Principal energy level 2, which corresponds to the second period, has two sublevels, an S, and then we also give it a P. Principal energy level 3, which corresponds to the third period, has an SP and a D. And then 4 through 7 would have 4 principal energy levels, an S, P, D, and F. All right. Each of those sublevels can hold a specific number of electrons. So the S sublevels can hold a maximum of 2 electrons. A P can hold a maximum of 6 electrons. A D can hold a maximum of 10, and then an F can hold a maximum of 14. Okay. All right. Each of those orbitals or probability areas too have their own specific shapes, which should be, hopefully you learned about this before too, so this should be review. But an S is going to have a spherical shape, P is going to have a dumbbell shape, a D would look like a double dumbbell, and an F would look like, you could say, a flower. And here's pictures too of all of them in their orientations. An S has one orientation. A P has 3 orientations. You can orient that P orbital along the X, Y, or Z axis. A D would have 5, and then an F would have 7. Now, when you're filling these orbitals, you need to follow several rules. First, you fill the lowest energy orbitals first. So like we would start with the 1s and then move to the 2s and then move to the 2p. We call that the off-ball rule. Then you also will have to obey Hund's rule and the Pauli's exclusion principle. So what those tell us is you fill in each individual orientation first and then go back and double up. And also electrons are going to spin in the opposite ways. So if you're looking at the orbital notation, you'd have one arrow up and one arrow down. We're not going to be drawing orbital notations. We're just going to focus on electron configurations. So let me jump to electron configurations. Now, we previously said that first principal energy level has one electron, or one sublevel. The second principal energy level has 2 sublevels, an S and a P. The third has 3, S, P, and D, and so on. And each of those sublevels has a certain number of electrons they can hold. If you use the periodic table and look at how it's purposefully separated, you can determine all those values and tricks without really having to memorize everything. So what I mean by that is, on the far left side of the periodic table, there's 2 groups or 2 families that are kind of like split off over there. These first 2, the alkali metals and the alkaline earth metals, correspond to the S sublevels. Okay? If we jump across, so pass up the transitions and move over to the next section, we have 6 groups over here, and I'm going to cut off helium for a reason I'll explain in a minute. And those 6 groups correspond to the P, right? Because P can hold 6 electrons. In the transition family, there's 10 groups across. So we have the D sublevels represented here in the transitions. And then the lanthanides and actinides by themselves at the bottom, there's 14 across, so that stands for the F. So again, going back up here to helium, we cut off helium because helium actually ends in the 1s sublevel. So it would kind of fit over there by hydrogen, but we put it over here with the noble gases because its outer valence level, that 1s, is filled. So it really does belong with the noble gases. All right. So when you are writing the electron configuration for elements, you start at the beginning with hydrogen, and you would write each combination of principal energy level and sublevel, but you only write the highest exponent or superscript for every sublevel. What that means is, let's jump to an example and say we're looking at aluminum. Say we're looking right here at aluminum and writing its electron configuration. We'd start up here with hydrogen. You read left to right. When you get to the end of the line, you jump down to the next line. So hydrogen, we have a 1s1, and then over here, helium would be 1s2, because it's the second one in that 1s sublevel. However, from both of those, because it's the same sublevel, a 1s, you only write the highest exponent. So for aluminum, we're going to have so far 1s2. Then we move down to the second row. We have a 2s1 and a 2s2. Again, you're only going to write the highest exponent. So we would write 2s2. Moving across, now we're in the 2p's. So we have 2p1, 2, 3, 4, 5, 6. But again, you're only writing the highest exponent. So 2p6. Moving on down, we have the 3s's. We have 3s1, 3s2. Only write the highest exponent, so 3s2. Then moving across, aluminum, we're in the 3p1. So we would write 3p1. And that's the full electron configuration for aluminum. You could also check yourself, because aluminum, when it's a neutral atom, should have 13 electrons. If we were to add up these exponents, and the exponents are representing the electrons in each of these sublevels, we would have 2 plus 2 plus 6 plus 2 plus 1 would give us 13. So when you add up all of the electrons, it should equal the number of, or when you add up all the exponents, it should equal the number of electrons the neutral atom would have there. Okay. All right. Let's look at one more. Let's do copper. Copper we would find right here in the transitions. So starting up here, first row, we have 1s, 2. The second spot, we would have 2s2. Moving over, we have our 2p's. We've gone through all of them, so we'll write 2p6. Then we have 3s, so 3s2. Moving over, we have 3p. We have all those p's, so 3p6. Then we have down here 4s2. Now remember here, even though this is the fourth row, the fourth period, and the fourth principal energy level with this 4s, the transitions have to, like these D blocks, move in another principal energy level, because remember that third principal energy level has to have 3 sublevels. In SP, there's one more, so we have to have our D. So instead of being 4D here, it actually moves in and it's 3D. So we would have 3D9. And that's the full electron configuration for copper. Now, let's see. Here's a few more examples if you wanted to take a look at them. And like I said, we're not going to focus on orbital diagrams. All right. If the exam question doesn't specify, like if it doesn't say write the full electron configuration, you are able to write the noble gas configuration. And as a review on noble gas configurations, what you do for those is you put the noble gas, or closest noble gas, before the target element. You put its symbols in the brackets, and then you finish the electron configuration. So if we go back to that copper example, Cu, what we would have is to find the closest noble gas to copper that comes before copper. So in this case, that's going to be argon. So we would put argon symbol in brackets. And then that allows us to get a head start right in the spot where argon is found. So we'd start at argon, move down, and we have 4s2. And then going all the way out to copper, we have 3d9. So it's essentially a shortcut or an abbreviated way to write the electron configuration. And like I said, if the question says write the electron configuration, but they don't specify the full, you are welcome to do the noble gas configuration. But if it specifically says write the complete electron configuration, you cannot use the noble gas configuration. You got to write the full thing. All right. There's some more examples with noble gas configuration. And some more here too, if you wanted to take a look at them. And one thing too, I do want to point out is when we're looking at electron configurations of ions. Remember, if we're looking at ions, so cations would gain electrons and then anions would lose electrons. So when you're writing the electron configuration for these ions, you're going to either add in or remove electrons from the outermost energy level, that outermost shell. But an important part of this, an important note here, is that the D block elements are going to lose their last S electrons before you take away the D electrons. So, for example, let's suppose we're looking at Fe2+. Fe2+, regular iron, so let's write that over here. Iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6. So if we're comparing iron to iron 2+, this 2+ tells us that it has lost 2 electrons. So it has lost 2 electrons. So that means we have to get rid of 2 of the electrons in this configuration. And what we're going to do is take it away from the outermost shell. This 4s2 here is in a higher principal energy level. We're going to remove this 4s. So even though you filled in the 3d after the 4s, you take away, for transitions, the D block elements, you take away their outermost s before you move into the D, okay? And before you take away any of those D block electrons. So we lost 2 electrons. We're going to kick off both of those 4s's, so that's going to give us 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. So that would be the electron configuration for Fe2+. It would be incorrect to say 3d4 and leave on the 4s2. That would not be correct. Now, if it was Fe3+, then we would take away those 2 electrons from the 4s, and we still then would have to take away 1 more. So in that case, we would then take away that 3d, one of those 3d electrons. All right, here's another example with manganese. So regular manganese, when it's a neutral atom, has this electron configuration here. When we're looking at a manganese with an ion with a 2+ charge, we would take away 2 electrons from its configuration, and we always take away the s before we move into the D. So in this case, we would just take away those 4s2. All right, and then here's another example. So say if we're looking at chloride, like the chlorine ion with a -1 charge, then here, chlorine typically would be 1s2, 2s2, 2p6, 3s2, 3p5. So this time, since we have a -1, we're adding in an electron, so we added into the outer one. So we'd add in the 3p5, we would add 1 more to give us 3p6. And then there's some more examples there. All right, that is all for this video.